the lecture series on differential equations for undergraduate students. Today's lecture is on Fourier transforms. In last lecture, we had learned about Fourier sine transform and cosine transform. If you remember, Fourier cosine transform for any function f we have defined as 2 upon pi integral 0 to infinity f x multiplied with cos omega x integrated with respect to x, that is we are getting a function with respect to omega. Similarly, sine transform for any function f was 2 upon pi integral 0 to infinity f x sine omega x integrated with respect to x. Today let us try to find out some important properties of these functions. So, first, existence. If f x is absolutely integrable positive on x axis and piecewise continuous on every finite interval. We have seen that this property, what does they mean? That it is integrable positive on x axis and piecewise continuous on every finite interval. Then Fourier cosine and Fourier sine transform of the function f x does exist. So, this gives the existence of Fourier sine and Fourier cosine transform. Yes. So, next property is linearity. Let f and g are two functions for which Fourier cosine and sine transform exist, that is f c hat omega, g c hat omega and f s hat omega, g s hat omega does exist. And let for any constants a and b define a new function h as a times f x plus b times g x for every x. Then if I try to find out the Fourier cosine transform of this new function h, what it would be? By definition it will be 2 upon pi integral 0 to infinity h x cos omega x dx. Now h x is nothing but a times f x plus b g x. So, let us substitute it, we get 2 upon pi integral 0 to infinity a times f x plus b g x cos omega x dx. Now, using the properties of definite integral, we can write this as the two integrals 2 a upon pi integral 0 to infinity f x cos omega x dx plus 2 b upon pi integral 0 to infinity g x cos omega x dx. Now, these integrals are nothing but the first one is nothing but the Fourier cosine transform of f x and the second one is nothing but the Fourier cosine transform of g. So, we do have it as a times f c hat omega plus b times g c hat omega. Similarly, if I try to find out the Fourier sine transform of h, by definition it will be 2 upon pi 0 to infinity h x sine omega x dx. Now, substitute the value of h, that is as a f plus b g, we get it as 2 upon pi integral 0 to infinity a times f x plus b times g x multiplied with sine omega x integrated with respect to x. Now, again using the properties of definite integral, break it into two integrals. One is a times 2 upon pi 0 to infinity f x sine omega x dx, another is b times 2 upon pi integral 0 to infinity g x sine omega x. Now, the first integral is nothing but the Fourier sine transform of the function f and the second integral is the Fourier sine transform of g. So, what we have got it as a times Fourier sine transform of f, that is f s hat omega plus b times g s hat omega. Thus, what we had learned that if Fourier sine and cosine transform does exist, then Fourier cosine transform of a f plus b g, that is linear combination of f and g, is nothing but a times Fourier cosine transform of f plus b times Fourier cosine transform of g. Similarly, for Fourier sine transform of a f plus b g is same as a times Fourier sine transform of f plus b times Fourier sine transform of g, that is these transform Fourier sine transform and Fourier cosine transform, they are linear, they contain or they take up the property linearity property. Another property, Fourier sine and cosine transform of derivatives, that is if the function is differentiable, what will be the Fourier sine or cosine transform of derivatives. So, the first result is let f x be continuous and absolutely integrable on x axis, and let the derivative of f, that is f dash x, be piecewise continuous on each finite interval, and moreover f x approaches to 0 as x approaches to infinity, then the Fourier cosine transform of f dash x, that derivative of x, is given as omega times Fourier sine transform of f minus 2 upon pi f of 0, and Fourier sine transform of f dash x is minus omega times Fourier cosine transform of f x. Now, let us prove this result or find out, that is how it is happening. So, Fourier cosine transform of f dash x, by definition it should be 2 upon pi 0 to infinity f dash x cos omega x dx. Now, integrate it with integration by parts, taking f dash x as the integrable function and cos omega as the differentiation function, second function. So, it would be 2 upon pi f x cos omega x 0 to infinity plus omega times 0 to infinity f x, derivative of cos omega is sin omega and omega is outside, minus sin omega. So, plus 0 to infinity f x sin omega x dx. Now, first evaluation, since f x approaches to 0 as x approaches to infinity, so at infinite it would be 0. Now, when x is 0, f x is f 0 and cos omega x, that is at x is equal to 0, is 1. So, what we would be getting is the 2 upon pi minus f upon 0, 2 upon pi f 0 from here, and this is nothing but the Fourier sine transform of f. So, omega times Fourier sine transform of f, this is the first result we have got. And Fourier sine transform of f dash x, by definition it is 2 upon pi integral 0 to infinity f dash x sin omega x dx. Again we will go with integration by part. So, it would be 2 upon pi f x sin omega x evaluated from 0 to infinity minus omega times integral 0 to infinity f x cos omega x dx. Now, as we do know that as x approaches to infinity f x approaches to 0. So, as x approaches to infinity this function will give us 0. At x is equal to 0, sin 0 is 0, that says this particular function is, or this part is not giving us anything over here, it is 0. What is being left is minus 2 upon pi omega 0 to infinity f x cos omega x dx, which is nothing but the Fourier cosine transform of f. So, we have got minus omega times Fourier cosine transform of f. This is the result we have got. So, we have proved this result. Now, let us come to the extend these results to the second derivatives, this derivative results. So, we says we are interested in finding the Fourier cosine transform of second derivative of f. Now, use the previous formula which says is that it should be the omega times Fourier sine transform of its integral, that is first derivative f dash x minus 2 upon pi f dash at 0. Now, what is the Fourier sine transform of f dash x? We would use the formula, it is minus omega f c, that is Fourier cosine transform of f. So, minus omega and omega I got minus omega square Fourier cosine transform of f x, and the second term is as such minus 2 upon pi f dash 0. Similarly, the Fourier sine transform for f double dash x, that is f s Fourier cosine sine transform of second derivative of f x, using the formula for first for the f dash, we get it minus omega times Fourier cosine transform of f dash x. Fourier cosine transform of f dash x is omega times Fourier sine transform of f x. So, this minus omega square Fourier sine transform of it should be Fourier sine transform of f x minus 2 upon pi So, minus minus sign will get plus 2 upon pi with omega 2 omega upon pi f at 0. So, we have got, that is, in the first derivative Fourier cosine transform is changing to the Fourier sine transform, in the second derivative Fourier cosine transform is changing to the Fourier cosine transform. Fourier sine transform here in the first derivative is changing to the Fourier cosine transform, and in the second derivative it is changing again to the Fourier sine transform. Let us just try to use this formula for solving some problem or evaluation of some transforms. Find the Fourier cosine transform of the function e to the power minus ax for x positive. Now, how we are going to find it out? Fx is e to the power minus ax. So, f dash x is minus a times e to the power minus ax, and f dash 0 is minus a. F double dash x would be a square e to the power minus ax. What we are getting is fx, f double dash x, we are just getting the constant difference, that is a square times fx. So, Fourier cosine transform of a square fx. A is a constant. So, by the properties of linearity it would be nothing but a square times Fourier transform of fx, and a square fx is f double dash x. Now, I use the formula for Fourier transform of second derivative of f, that says it should be minus omega square Fourier cosine transform of f plus 2 upon pi f dash 0. F dash 0 would be, from here we had already calculated, it is minus a. So, what we have got now, here it is linearity property. So, what we have got finally actually, that a square times Fourier cosine transform of fx is same as minus omega square times Fourier cosine transform of fx plus 2a upon pi. Now, take this part over here, that is Fourier cosine transform, it is a square plus omega square. So, what we have got, the Fourier cosine transform of fx as 2a upon pi divided into a square plus omega square. This term we have taken this side. So, it is a square plus omega square times Fourier cosine transform of fx is 2a upon pi. So, we have got the Fourier cosine transform of fx as 2a upon pi into a square plus omega square. Now, you see we have not evaluated any integral over here. Using these properties we can find out the Fourier cosine transform of this function more easily. Now, come to the Fourier transforms. Before coming to the Fourier transform, let us have, as we have done in the Fourier series, the complex form of Fourier series. Let us just move to the, because we had find out the Fourier sine transform and Fourier cosine transform when we have converted the Fourier sine series or Fourier series into the integrals. Now, let us convert the complex form of the Fourier series into integral. So, complex form of Fourier integral. Let fx is we do know 0 to infinity a omega cos omega x plus b omega sin omega x d omega, where we do know that a omega is 1 upon pi minus infinity to plus infinity f t cos omega t dt, and b omega is 1 upon pi 0 to infinity f t sin omega t dt. This we had done in the Fourier integral. So, fx we can write as 1 upon pi. Now, I am writing this a omega and b omega inside over here. So, this integral 0 to infinity as such, with a omega I can write minus infinity to plus infinity f t cos omega t and then cos omega x. Similarly, here the integral would be 1 upon pi, that is again common, 0 to minus infinity to plus infinity, that is I have joined the two integrals because the properties of definite integral, these we could write as a one single integral f t sin omega t and sin omega x. So, f t again I have taken common, and this term has come as cos omega t cos omega x plus sin omega t sin omega x dt d omega. Let us simplify it. This is 1 upon pi 0 to infinity. Now, what this inside this integral of what I have got, cos omega t cos omega x plus sin omega t sin omega x. If we see, this is nothing but cos of omega x minus omega t, or you could call omega t minus omega x, because cos of minus x is cos of x. So, it does not make any difference, but we will write it at cos omega x minus cos omega t. So, this is integral minus infinity to plus infinity f t cos omega x minus omega t dt d omega. Now, cos is as cosine is an even function. So, this is the formula which we had used. So, what we have got, we can write it as 1 upon 2 pi minus infinity to plus infinity, because it is even function. So, that says is I can use the integral 0 to infinity. Let us come back again to the previous slide. See, here this cosine is an even function. Now, if I integrate it, this complete function would be actually even with respect to omega. If we see this complete function is, because f is not containing the term of omega, f is with respect to t, the omega is coming in the cosine function, and cosine is an even function. So, with respect to omega, this integral would be a function of omega, and that is an even function. And using the properties of definite integral, which says is that if a function is even, then integral minus a to plus a of an even function f we can write as 2 times 0 to infinity or 0 to a. So, now I am using that property in the reverse order. So, what we get 1 upon 2 pi, this integral now you see is I am writing minus infinity to plus infinity, minus infinity to plus infinity f t cos omega x omega t dt d omega. Now, in the similar manner, if I take this integral f t sin omega x cos omega t dt. Now, what I have done is this integral I have not found out from anywhere. Here, rather than this cosine function, I had used this sine function. Now, this sine function in the omega, this is an odd function. So, if I write this integral, then this inside integral is an odd function of omega. Using the properties of definite integral, this integral must be 0. So, now since this integral value is 0, I can add up over here in this f integral, that is f x plus 0, it will not give anything, but in the integral form if I am using with, now what is we are trying to do is we are trying to make a complex form of Fourier integral. So, I would use it with the imaginary part. So, now rewrite these integrals adding I, that is square root of minus 1. I can write f x as 1 upon 2 pi integral minus infinity to plus infinity, that is outside, then integral minus infinity to plus infinity f t, in both these one it is common. Here I am writing is cos omega x minus omega t plus I times sin omega x minus omega t dt d omega. So, what I have done is I have added these two integrals with plus I sin, because this is 0. So, it would be same as f x. But now what I have got inside this bracket, this is cos omega x minus omega t plus I times sin omega x minus omega t. Now, if you do remember our complex exponential function, this can be given as e to the power I omega x minus omega t. So, f x would be 1 upon 2 pi minus infinity to plus infinity f t e to the power I times omega x minus omega t dt d omega. Now, you see that we had written this function in the form of integral with complex function. So, this is called the complex Fourier integral. So, complex Fourier integral we had find out as 1 upon 2 pi minus infinity to plus infinity integral again minus infinity to plus infinity f t e to the power I omega x minus omega t dt d omega. Now, let us simplify this double integral again. This e to the power I omega x minus I omega t I can write as e to the power I omega x into e to the power minus I omega t. So, we are getting it this 1 upon 2 pi as such, one integral with respect to t, another integral with respect to omega. So, first the integral, because omega t, both the omega and t are coming over here. So, we would write it here. So, it is f t e to the power minus I omega t, it should be minus I omega t dt into e to the power, now this is the function of omega only because t is been integrated out, into e to the power minus I omega x d omega. So, now what we are getting is this inner integral we would call, because this is a function of omega, we would denote it as f hat omega minus infinity to plus infinity f x e to the power minus omega x d omega. Now, you see is that is t I have changed with x. This is called the Fourier transform of the function f, and now write this f x as 1 upon 2 pi integral minus infinity to plus infinity. This inner integral is nothing but the Fourier transform of f. So, f hat omega e to the power I omega x d omega, this gives me the function back at x. This is called the inverse Fourier transform for the function f hat omega. So, what we have got, that is using the complex form of Fourier integral, we had represented the function f as double integral here, where the inner integral was with respect to the function variable, and we are getting it as a function of another variable omega, and the outer integral is with respect to that another variable omega and giving back me the value of the function at the first variable x. Now, let us come to the properties of this function. First is existence of Fourier transform. The sufficient condition for existence of Fourier transforms are f x is a piecewise continuous on every finite interval. Second is that f x is absolutely integrable on x axis. As we have seen, that is the conditions for existence of Fourier integrals, the existence of Fourier series, and the existence of Fourier cosine and sine transforms. What we have done when we have obtained this all this complex form of Fourier transform, we had used many places, that is interchange of the integrals, the limit that it is existing, and so on. So, all those things mathematically it is a little bit difficult to prove and to find out those things, and it would be beyond the level of this course. So, I am not going to that particular things. Here I am just giving you one result which says the sufficient conditions for existence of Fourier transform. That is what we want, that is to exist those limits and to exist those integrals. So, first condition is that my function has to be piecewise continuous, and second is that it should be absolutely integrable. Let us try one example to find out the Fourier transform of any given function. Question says, find the Fourier transform of the function f which is x in the interval 0 to a and 0 otherwise. Let us find it out. Fourier transform of any function f hat omega by definition is integral minus infinity to plus infinity f x e to the power minus I omega x dx. Let us try to find it out. Here this integral function is defined in the range 0 to a as x and it is 0 otherwise. So, this integral would change to 0 to a x times e to the power minus I omega x dx. Let us integrate this by parts. What we get? E to the power minus I omega x upon I omega x times evaluated 0 to a plus 1 upon I omega integral 0 to a e to the power minus I omega x dx. Now, evaluate at x is equal to a, it would be e to the power minus I omega and this would be a. So, I would be getting is, and 1 upon I is minus I. So, we would be getting is I times a upon omega e to the power minus I omega, and at x is equal to 0 this would give me 0 plus this integral of e to the power minus I omega x is minus e to the power I omega x upon I omega. So, I square omega square and I square would give me 1 minus 1. So, plus 1 upon omega square evaluated at, so e to the power minus I omega and e to the power minus I 0, that is 1. So, we do get e to the power minus I omega a minus 1. Let us rewrite it. What we have got, e to the power omega 1 upon omega square e to the power minus I omega plus I a upon omega times e to the power minus I omega minus 1 upon omega square. Again rewrite it in a more simplified form, that is, here I have taken 1 upon omega square common. So, e to the power I omega would be here 1 plus I a omega and this omega square outside, so this is minus 1. Now, you see it is a complex valued function. So, the Fourier transform is a complex valued function. When we practically use, we normally take this real part and imaginary part separately also for the practical purposes, but that part we will do later on when we would go for the practical purposes. Here we are just doing the definition and understanding these transforms. Let us do one more example. Find the Fourier transform of the function e to the power minus a x square for x in the real line and a positive. F at omega, by definition minus infinity to plus infinity f x e to the power minus I omega x dx. The function is defined on the whole real line. So, it is e to the power minus a x square e to the power minus I omega x dx, which is rewriting it as e to the power minus a x square plus I omega x dx. Now, we are having in the exponent as the square function. So, we will make it whole square. For that we will go write it as minus a x square. So, this minus is outside, this inside one I will try to make it as whole square, a x square plus I omega x. It would be whole square if I do have this I omega that it should be. So, I want I square omega square by 4 and a is here. So, it should be minus omega square upon 4a plus omega square upon 4a, because we have just subtracted. So, we have to add it. Now, again simplify it. What it says is e to the power minus omega square upon 4a, that I have taken outside because this integral is with respect to x, and here it is integral of e to the power minus. Now, what is this function? This function has come up as square root a times x plus I omega upon 2 by root a whole square, integral it of it with respect to x. This integral is equal to square root pi upon a e to the power omega square upon 4a for a positive. That says is we had not evaluated this integral over here. We will see it later on, that is how it is coming. What we are getting the result, that is Fourier transform of e to the power minus a x square is square root pi upon a e to the power omega square upon 4a for a positive. Now, let us see the evaluation of this integral. This is not a very easy integral. Let us see that is how we are evaluating this integral. So, let us say that I is this integral minus infinity to plus infinity e to the power minus square root a times x plus I omega upon 2 upon square root a whole square dx. We want to show that this integral is square root pi upon a. Let us just try with I. Let us take this whatever is the quantity here, that is square root a times x plus I omega upon 2 by square root a as y, then dx would be 1 upon square root a dy. So, I would be 1 upon square root a minus infinity to plus infinity, because as x approaches to minus infinity, y would also approach to minus infinity, because all these things are constant, and as y approaches to plus infinity, this x approaches to plus infinity, y would also approach to plus infinity. So, this integral is 1 upon square root a minus infinity to plus infinity e to the power minus y square dy. Now, double this integral or make this square, that is I am multiplying I with I. Multiplication of integral, that simply says is I can 1 upon square root a into 1 upon square root a, that is 1 upon a, and the integral 0 to infinity e to the power minus y square into the integral 0 to infinity e to the power, let us say with another variable, so that there is no confusion, e to the power minus z square dz. Now, what we are taking is that this multiplication as the double integral now, because that is simply the double integral. So, what we have got 1 upon a minus infinity to plus infinity minus infinity to plus infinity integral e to the power minus y square minus z square dy dz. Now, let us change these Cartesian coordinates into the polar one, that is using r square as y square plus z square and tan theta as z upon I y. So, r and theta. We do know by the change of integration, that is change of variable, the Jacobian gives me that dy over dz would be changed to r dr d theta. So, the I square would become now 1 upon a as such, and this limit, if you to remember, or you could just see, is that is what we are doing is we are changing this, this is on the whole Cartesian space, that is on the whole space. Now, for whole space, if I try to change it to the polar one like this one, so what we say is that is I have to take the r to be all real numbers, that is 0 to infinity, and my theta should take the whole orientation 0 to 2 pi. So, it is 1 upon a 0 to 2 pi 0 to infinity r is coming from this dy dz is r dr d theta, and this is e to the power minus r square. So, r times e to the power minus r square dr d theta. Now, let us consider this integral 0 to infinity r e to the power minus r square dr, because there is no function of theta. So, this we can integrate with respect to r. No. So, if I take e to the power minus r square, its derivative is actually minus 2 r e to the power minus r square. So, what we could say is r e to the power minus r square is nothing but the antiderivative of the thing. So, let us make it as, first if I integrate it with respect to theta also, that is here I think is I have done this first integration with respect to theta. So, this integral we are going to evaluate, we see this integral, we do have this function as r e to the power minus r square, it does not contain any element of theta. So, the first integral if I do take 0 to infinity r e to the power minus r square dr, this can be evaluated separately, and another integral 0 to 2 pi with respect to theta, that can be evaluated separately with a constant. So, let us first evaluate this simple integral, that is with respect to a constant. So, what it will give me? It will give only 2 pi. So, we got 2 pi upon a 0 to infinity integral r e to the power minus r square dr. Now, let us see this function. If I take e to the power minus r square and find out its derivative, it would be using the chain rule minus 2 r times e to the power minus r square. What it says is that r times e to the power minus r square is nothing but the antiderivative of some constant times e to the power minus r square. So, what it would be? This 2 pi upon a is as such, and this is the antiderivative of minus 1 by 2 e to the power minus r square, that is its integral is minus 1 by 2 e to the power minus r square, evaluated from 0 to infinity. Now, at infinite, as r approaches to infinity, r square will also approach to infinity, that says is e to the power minus r square, that is approaching to 0, this we do know from the limit. So, as r approaches to infinity, this function will give me 0, as r approaches to 0, this will give me 1, that is minus half. So, what I would get it as actually multiplied minus half and minus sign will cancel it out. So, it is 1 upon 2 only. So, it is pi upon a. So, what we have got I square as pi upon a. So, I would be square root of pi upon a, and that is what we had substituted in the earlier integral to find out the Fourier transform of the function. So, you see that is Fourier transform of the function, this kind of exponential function which are very easy, but if it is square one, this is a little bit tedious to integrate. Let us see the properties of the Fourier transforms, which will help us in finding out the Fourier transform as well as in finding out some other things also. First property, as in the terms of linearity, as we have seen in the Fourier cosine and Fourier sine transforms also. Here the Fourier transform is a linear operator, that is for any f and g whose Fourier transforms are existing, that any two functions f and g for whose the Fourier transform does exist, the Fourier transform of a times f plus b times g is nothing but a times Fourier transform of f plus b times Fourier transform of g. For proving it, it is very easy. We could see this can be written in another notations also, but this notation says is that Fourier transform of a f plus b g at omega is same as a times Fourier transform of omega plus b times Fourier transform of g at omega. Any of these two things can be written, we just have to understand that it is linear. Proof was easy, so I had left for you to do by yourself. Here is the Fourier transform of derivative. Let f x be continuous on x, and here again we are assuming that f x is approaching to 0 as x approaches to either minus infinity or plus infinity, and further we are assuming that f dash x is absolutely integrable on x. Then the Fourier transform of derivative of f, that is f at f dash, the Fourier transform it at omega is nothing but I times omega times Fourier transform of f. Let us try to prove it. Go with the definition of Fourier transform of f hat. By definition, it is minus infinity to plus infinity f at x e to the power minus I omega x dx. Let us go to the integrate it by parts, taking f dash x as the integrable function. So, what we get f x into e to the power minus I omega x evaluated from minus infinity to plus infinity plus f x, and derivative of this is minus I omega times e to the power minus I omega x. So, here it would be plus I omega times integral minus infinity to plus infinity f x e to the power minus I omega x dx. Now, this is same as I times omega times f hat omega from here, because I omega is as such and this is nothing but the Fourier transform of f. What happened to this part? You see, we had assumed that f x is approaching to 0 as x is approaching to either plus infinity or minus infinity. So, when x is approaching to minus infinity, this is of course approaching to the plus infinity, but f x is approaching to the 0, and that give us, that is if we just go that this would be or rather we are assuming that this is fastly going to the 0 than this is going to infinity. So, this multiplication goes to 0. When x approaches to infinity, this is approaching to 0 as well as this is also approaching to 0. So, both the time it is giving us 0. That is what we have got, that the Fourier transform of the derivative is nothing but I omega times the Fourier transform of the function. Now, let us extend this result for the second derivative. What it says is, that is if I take the Fourier transform of the second derivative using this formula, it should be I omega times the Fourier transform of the first derivative. Again use this formula which says it should be I square omega square times the Fourier transform of omega. Now, I square is nothing but the minus 1. So, what we have got, it is minus omega square times f hat omega. Now, you see that is how we can use this property for evaluation of some Fourier transform. Find the Fourier transform of f x, x times e to the power minus a x square, x belonging to whole real line and a is positive. You remember that is just now we had find out the Fourier transform of e to the power minus a x square. That was not very simple, we had to evaluate one integral which was a little bit difficult. Now, here we are having the function x times that one. How we are going to proceed it? We will use this property just now we had obtained about this Fourier transforms. F of x is given as x times e to the power minus x square. Just when we had evaluated that integral, we had find out that is if I take e to the power minus x square and its derivative, I would get minus 2x times e to the power minus x square. That says this is actually half time integral, or sorry, the derivative of e to the power minus x square. Let us write this function e to the power minus x square as f1. So, what we are getting is minus half times f1 dash x. Now, f1x is your e to the power minus x square. Just now we had evaluated the Fourier transform of e to the power minus ax square. Now, there if I take a to be 1, that would be the same as e to the power minus x square. What the integral we had evaluation we had find out? If you do remember it, that was square root pi by a into e to the power minus omega square by 4a. Now, a is 1. So, what I would get here the Fourier transform of this f1 omega, that is Fourier transform of e to the power minus x square as square root pi e to the power minus omega square by 4. Now, so Fourier transform of f is nothing but minus half times Fourier transform of f1 dash. Now, use the property of linearity and property of this derivatives. So, what would be f hat omega? First, using the property of linearity, we would get is minus half times the Fourier transform of f1 dash. What is the Fourier transform of f1 dash? That is, just now we had find out the Fourier transform of dash is nothing but I omega times the Fourier transform of f. So, this minus half is as such, the Fourier transform of f1 dash omega is I omega times f1 dash Fourier transform of f1 at omega. The Fourier transform of f1 at omega we had find out, that is it was square root pi e to the power minus omega square by 4. So, put it out here, minus I omega by 2 square root pi e to the power minus omega square by 4. Now, you see is without doing that integration again, we have come up with the solution. So, that says is that is we could get the Fourier transform easily if we use these properties. There is one more very important and interesting property about this Fourier transform, which is called the convolution property. That is again being used to find out the Fourier transform of complex functions. Complex means not that complex form, that is for the difficult functions, we can break them as convolution and then we can find it out. So, let us see what is called this property convolution. The convolution of the function f and g is defined as, denoted by f convolution g. Here this is star is the notation for convolution. This is defined as minus infinity to plus infinity f y g x minus y dy. This is at point x, we are integrating with respect to y. So, what one function we are taking is f y, another function we are taking is g at x minus y. Now, if I interchange the at the change of variable, if I take, that is if I assume that z is equal to x minus y, I can write this as integral minus infinity to plus infinity f of x minus y g y dy. What it says is this convolution is actually your commutative, whether you are writing f first or g first, that does not matter. F convolution g is same as g convolution f. This is actually integral of the first function at some point multiplied with the another function at the point x minus that first point and evaluated with respect to that point, then we are evaluating it at function at that point x. What is the convolution theorem which we are calling this for the Fourier transform? You see, first assuming that f x and g x are piecewise continuous, bounded and absolutely integrable on x. You see why these conditions we are writing? Because we want that for Fourier transform to exist, we do have two conditions, that it should be piecewise continuous on every finite interval and it should be absolutely integrable on x. So, these two properties just simply give me that is the Fourier transform does exist. Then the Fourier transform of f convolution g. Now, you see f convolution g is this function, the integral can be given as multiplication of Fourier transform of f and Fourier transform of g. So, here what is in the function 1, this is integral, that is convolution. In the Fourier transform, that is in the omega 1, it is changing to the only the multiplication of the Fourier transform. That says is it would be very easy. Now, let us see the proof of this theorem, that is how it is saying is. Let us just start with this, the Fourier transform of f convolution g. By definition, it should be the integral minus into plus infinity f convolution g at x e to the power minus I omega x dx. Now, let us write this f convolution g at x, that is again another integral. So, it should be first integral is as such minus into plus infinity, this is integral minus into plus infinity f y g at x minus y dy e to the power minus I omega x dx. Now, let us write it this as double integral minus into plus infinity, another one also minus into plus infinity f y g x minus y into e to the power minus I omega x dy dx. Now, let us make the change of variable as x minus y as z. This says is x would be y plus z. So, now we are just changing this x minus y to z. So, x is changing to the y plus z. So, dx would be nothing but dz, that is how we are doing it. Y we are keeping a constant when we are transforming only with respect to x. So, y we are not treating as another variable, we are just changing only one variable x. So, as x is approaching to minus infinity, z will also approach to minus infinity, as x is approaching to plus infinity, z will also approach to plus infinity for any fixed y. So, this integral is minus into plus infinity inside function minus into plus infinity integral f y, this g x minus y, that is z e to the power minus I omega x is being changed to y plus z dz dy. Now, minus into plus infinity, this now we are getting is these two integrals as here is one function is with respect to y only, another is with respect to z only. Here also we can break it into as e to the power minus I omega y and e to the power minus I omega z in the multiplication. That is, we can break this double integral into actually the product of two integrals. What are those? Minus into plus infinity f y e to the power minus I omega y dy and integral minus into plus infinity g z e to the power minus omega z dz. Now, let us see what these integrals are. If we see this first integral, this is nothing but the Fourier transform of f and this is nothing but the Fourier transform of g. Now, these transform or these integrals exist because we had already assumed that f and g were piecewise continuous, integrable and bounded. That says is that this Fourier transform does exist or these integral does exist. So, this is nothing but f hat omega into g hat omega. So, what we have got the Fourier transform, this actually function is here you would see is that is in application how it is a very useful thing, that is rather than solving the problem in the actual space, if we go to the another variable, that is the transform function, and there we can solve the problem and then we can come back, because in the Fourier transform we had also seen is that how to find out the inverse Fourier transform. If Fourier transform for this any function f is integral minus infinity to plus infinity f x e to the power minus I omega x dx, then the Fourier inverse Fourier transform of f hat omega was 1 upon 2 pi integral minus infinity to plus infinity f hat omega e to the power I omega x d omega. So, once we get this function, we can go back and find out its Fourier inverse transform, and then we can come back to our f convolution g. Rather than evaluating that integral, we may be sometimes may be more useful for getting the solution of the problems. So, we have learnt in these lectures a technique called the Fourier series are given by the Fourier, which said is that is any function we can make it out as that represent it as a sum of the series, which we called sum of the series of the containing the terms of sine and cosine, and we called it Fourier series. Then we have come up with some properties of those series, then sine series, cosine series, for the properties defined for those functions, some conditions for that functions are satisfying. We have learned that the Fourier series was applicable, or we could find out only when the functions were periodic. Then we want that is all the practical times the functions may not be periodic. We had extended that idea and we have come to the transforms. So, the first we had learned the Fourier sine transform and then Fourier cosine transforms. Then we had learned Fourier transforms as well. We will use these transforms and these series in solution of differential equations, that would be in coming lectures. We would learn about these things. You had already learned the Laplace transform like that. So, that is all for today's lecture. Thank you.